kindly turn on your cameras.
Hello. Hello.
I hope maximum participants have switched on their cameras. Okay, now we can. Seema ma'am, is the photo taken?
So shall we start?
Uh, Sir, we have some questions from the previous session. So
Yes,
if you
yes,
don't mind.
yes. I can see
So
there are two
yeah,
questions.
one of the question is where we can simulate RIS.
Okay, so since that we have one RIS controller, so RIS and base station are connected through RIS controller. So in most of literatures, we generally consider a perfect knowledge of CSI. And in that case, the base station design the beam forming, active as well as passive, and forward to the RIS controller. And through RIS controller, we control the direction for reflected signal. Is it clear? Hello.
Yes, sir. I guess yes. So one more question is there.
Yes.
If you can answer second one, how can we achieve a phase shift of 30-degree in a RIS?
Yeah. So see, we can't fix like this. So this is a manual. We are fixing 30-degree, but we say that RIS passive RIS, if you are considering, it will cover half space, 0 to 180-degree. So it depends on user. It will design the phase shift. So of course, if you know the exact location of RIS, just we can define the angle of the users, and then accordingly the base station or RIS controller will design the phase shift. Because when we define the this phase shift, so we have incident angle and reflected angle. So we define that angle. Let's say reflected angle at the 30 degrees. So if you define, then we can design the phase shift accordingly. Clear?
Sure. Yes, sir. Clear, sir. Sir, we can continue with the session number 6 now.
Okay. So let me share my slide. So can you see my slide?
Yes, sir. Yes, sir.
Okay.
Clearly visible.
Yeah. So in second session, now we want to utilize this machine learning or AI in order to design the full duplex, let's say MIMO communication or full duplex communication. So first of all, why we are going for full duplex? Why not the existing system is half duplex? So um, so we have some drawbacks of half duplex scenario. That means let's say if we have two operation uplink and downlink scenario by using the same resources, that means base station can't serve both kind of user at same time. So that means there may be a wastage of resources. So here, if you change or if you turn the operating mode of the base station from half duplex to full duplex, it will serve both kind of users. Some user may be uploading the videos, some user downloading the video, and the base station can serve this both user, both kind of user by using the same resources. So in another way, we can say that uh, we can achieve higher spectral efficiency or better resource utilization if you change the mode from half duplex to full duplex mode. So that's why the full duplex is going to be famous. So before 5 years or 5 6 years back, we are talking about full duplex will be part of 5G, but no, it's not possible. So then later on, we thought that it could be part of beyond 5G, or nowadays we are calling that advanced 5G. But it will not possible. So maybe it will. We will see full duplex scenario in a 6G communication or 6G. Yeah, in next generation, not 5G or beyond. So let's see why we go for 5G. What is the main? I mean, this full duplex case, as we have seen in the first session, why we are going for some advanced technology, RIS, IJAC, now this full duplex. So most important is mobile data traffic. As you have seen, the mobile data traffic by 2030, it will reach up to more than 5,000 exabyte per month. How we are going to meet? Either we have some resources, some extra spectrum government should allocate for this commercial purpose. So this is a one way, but the spectrum is very, very expensive. So we can't, government can't allocate a huge spectrum just for communication. So here, there is another way we can achieve or we can fulfill this requirement by adopting or developing some new technology in order to efficiently use the existing spectrum. So as we know that, we have several spectrum bands that are underutilized. So for example, if we say uh, this weather forecasting radar. So we are not using weather forecasting radar 24 by 7. Most of time you will see it will be in ideal mode. So we can use that spectrum for cellular communication. And similarly, this military. So again, they are not using all time. So we can use a spectrum that is spectrum for cellular communication. So for example, in US, this now the US Army has started sharing its spectrum with, for the cellular user or this commercial purpose. Of course, they are charging money, so they are making both money. Financially, they are getting benefit, and whenever they need, immediately they just withdraw this one. So there is some understanding between a service provider and the military radar operators. So here we have a certain, I mean, this 5G or 5G beyond. So the major requirement of mobile data traffic are like energy efficiency, or some other requirement like low latency. So all these requirements, motivate us to move to the new technology. So one of that is full duplex communications. But along with that, because everything, if you are inventing some new technology, so along with pros, you will also have cons. So we need to deal with that one. So we also have some challenges in order to implement this full duplex case. Because here I did not completely mix with the machine learning, but I will tell you how to use the machine learning. And if someone interested, so they can go through some on my website or IEEE, and they can read some of my paper where we have utilized DNN or some other machine learning technique in order to design the full duplex system. So in order to convert or use this full duplex technology, so one of major challenges can the self interference. How we are going to manage self interference? In another term, we call it leakage or interference temperature. So because the number of the transmitter and receive antenna at the same device, for example, base station, and we have limited distance between each antenna. So we can say ideally it should be lambda by 2. Um, so since the distance between transmitter and receiver will be very, very less, so the self interference power will be, the signal power will be very high. So how we are going to cancel the self interference power? If you can manage the self interference power, so um, we can double the throughput of compared to the half duplex case. So for example, if you are achieving, let's say 10 bits per second in case of half duplex, so full duplex will give 20 bits per second by using same resources. So some hardware, and but same time, let's say there are various part uh, that are hurdle in case of this full duplex. So one of this cancellation technique, hardware impairment, also imperfect CSI. So if you know perfectly, if you know the CSI, you can cancel. Okay. And various application of this full duplex where you are going to use like cellular systems. One of that is very, uh, powerful applications, cognitive radio, IoT scenario. Nowadays, it's a very, again, interesting and very hot research area where the IoT nodes um, can be operated in a full duplex mode. Also in energy harvesting, so this is another very good topic where the, let's say, device is harvesting the power and same time also communicating with the receiver. So doing both function at the same time. And another is multi-cell scenario. So where one cell operate in full duplex, uplink mode, another downlink mode again. This could be another scenario of this one. And the last one is part of hijack scenario. So radar LTE coexistence. So that means integration of two different systems and how to integrate such that this both systems should work perfectly. For example, the base station can operate in full duplex mode, or we can call in that case we can call dual functional base station. So by using same resources, the full duplex base station can detect the target as well as serve the users. So these are various applications we will see one by one. So So here the main motivation, if you see here, this is a Shannon capacity formula. We can say C equal to we have a bandwidth log base to 1 plus SINR. So this is a basic formula. Now this is, I mean, there are different ways to improve this capacity. Okay, in order to meet the mobile data traffic demand. So one is, let's say, we can divide the big network bit cell into heterogeneous network. That means small cells. So we can have, so we can, that one we call as a head net. So there could be, let's say we have a micro cell, a small cell, relay cell. Similarly, we have a femto cell. Again, we can go, the Wi-Fi like that. And due to that, the coverage range will become slightly higher. The signal strength at the edge user will become higher, and therefore the sum rate will become higher. Another, we can use more channel. Let's say at a base station, just increase the number of antenna. Let's say MIMO antenna. We have multiple antenna. We can go for massive antenna. And nowadays we have, let's say, we can go for let's say RIS element based antenna, massive antenna. We can through that we can improve the sum rate. And third point is, of course, if you have bandwidth, if you have a spectrum, just allocate more bandwidth. But we don't have. Okay, unfortunately, we don't have. So here we can identify some unutilized access millimeter wave, okay, especially higher spectrum RO level, for example, 100 gigahertz or more than 100 gigahertz. Spectrums are highly underutilized. So we can use that one for the communication, but most preferable is below 15 gigahertz. And that one is already allocated to various applications. So we have some limitation from bandwidth, of course, but heterogeneous network channels we can improve. And here inside this log base 2, here we can see we have power. So this is a you can say power, transmit power. The transmitter can increase the transmit power. However, as transmitter increase the transmit power, it will also impact on the interference. But we want this interference level, very low. It should be very low, and because here we have P over this is in denominator. If I become higher, then overall this term will become lower, so, and then capacity will become lower. So there should be balance between transmit power and this interference. So that means if we have some policy for this better interference management, we can achieve the higher throughput. So this is a graph, at least here we can see this is according to the ITU. We have seen this one in a first lecture. So here 5G, okay, in India, for example, this Geo or any, I mean, so most of companies, they are saying, also in Taiwan or US or UK, they are saying that they can provide, very high data rate, but we are not achieving. We are not getting that one. For example, here in a 5G or beyond, we are expecting 10 to 100 times higher data rate in terms of like more than 50 gigabytes or even higher, but we are not getting that one. Similarly, now if you see, because this is I mean, a changing or shifting from one current generation to next generation. So generally, it takes 10 years time. So in 10 years, we can expect, 10 to 100 times higher number of users. And due to that, the demand will become, I mean, very, very high. And here we can see we can expect 1000 times more data volume per unit area. And also in next generation, we are expecting higher energy efficiency, especially in terms of order of 100 times. So because we are looking for sustainable environment, and of course provide a higher bandwidth. So we can achieve these goals by using some technology. One is a MIMO. This one is now very famous. But again, this one is, we are not seeing this one in practical. Like still our mobile has a single antenna. But soon we are expecting at least we will see two antenna mobile with a two antenna, and then we can experience better signal quality, much better signal quality. Then we can start getting the 5G speed. So since we have limitation from the hardware, and but of course the service provider, they are just telling us, okay, we are providing 5G speed, but we are not getting 5G speed. Millimeter wave, this is another area. We can use higher spectrum in order to improve the throughput and full duplex. So this has ability to double the throughput of the current half duplex scenario. So for example, we have, if you look back, before 20 or 30 years, in most part of India, there was a single lane railway track. So you can say, if you are going from, let's say, one place to A to B and coming from B to A, so you could require, let's say, 2 days. But now due to 2A, maybe, just 50% of time. So here, if you manage this self-interference, so the full duplex system has ability to double the throughput of the current hub duplex. Some another technology, like we have non-orthogonal multiple access, or you can say under this we have various multiple access technique. We have let's say rate splitting or non-orthogonal multiple access. That is a part of multiple access technique. So this one is nothing but this will break the orthogonality in order to improve the spectral efficiency. Like previously we have OFDM. So in OFDM, that means we have dedicated resources, and due to that there could be a wastage of resources. So in order to control that wastage of resources, we can just break the orthogonality and use this NOMA, or let's say RSMA, or some other multiple access technique in order to utilize the spectrum in a more efficient way and improve the spectral efficiency. So let's see this example. I think this will be very interesting, especially you can easily understand the half duplex and full duplex. So here we have a set of uplink user, set of downlink user. We have one base station equipped with multiple transmit and multiple receive antenna. So here we can see this is a uplink user. So here, since base station operate in full duplex mode, its meaning is that base station, when it serve downlink user, it can't serve uplink user. When it serve uplink user, it can't serve downlink user. So here, for example, here if you see, it can operate in TDD mode, or time division duplex, or frequency division multiplex. So in TD mode, so let's say in T1, it received the data from uplink user. So it can't serve the downlink user. But in a next time slot, it will serve the downlink user, that is time T2. So it uses same resources, but at different time. So this is a one. Another is, let's say, FTD, frequency divisions, but here you can say there is a wastage of resources, and also time switching of the base station. First, it operate in receiving mode. Second, transmit mode. So again, there will be switching from receive to transmit mode. So there is a wastage of resources as well as switching. So frequency division, here you can say first of the base station receive through F1, and second here F2. Again, if you plot this one, this time scale plot, here you can see it can use transmit and receive, but different time slot, different frequency. So we have you can say dedicated is. So here frequency F1 and F2, but it's are all the time it receive, here it receive, and this is a transmit. So but they are orthogonal, kind of orthogonal. So again, wasted resource frequencies, and in order to control the inter-symbol interference, we need guard bands. So again, there will be a wastage of resources due to this. Now let's see full duplex case. How we can change this half duplex into full duplex mode. So let's say we have both in time division or frequency division. So at both, so base station operate in full duplex mode. That means when it is receiving data, same time transmitting. So that means serving both uplink user and downlink mode at same time, same frequency. So there is a no wastage of resources. But we will encounter with some problem, and the problem is here there will be self interference at the base station. We are using same resources, so it will also, because this is a transmit antenna and same time it is receiving, so it will also receive its own signal. So there will be self interference, and that will impact on the uplinks user, because this will work as an interference for uplink users. Now, apart from this, there is a second one, co-channel interference, because both system, this uplink user and downlink user operate at same time. So it will the uplink user will generate co-channel interference towards the downlink users. So here you can see we need to control these two problem, self interference and co-channel. If you can handle these two, then the full duplex you can operate at any places, and we can improve the spectral efficiency by double compared to the half duplex. So it's a very powerful tool, but now the problem is how we can control these two kind of interferences. Okay. So we have a state of art. So nowadays we have, since it started in 2010, so from the one group in Stanford University, and in 2010, Goldsmith, I think she was a assistant professor there. She pointed that full duplex is not going to be, you know, in a reality. So at later on, the Rice University, another group, they developed some analog cancellation technique. I mean, this self-interference cancellation in an analog domain, and they cancel around 70 dB of self-interference. And then other groups, they started working on this full duplex, and they realized yes, full duplex will be part of 5G or 6G. So now we are expecting this full duplex will appear in 6G. So this is some example of this full duplex scenario. Let's say first one, we have a full duplex uplink and downlink, so the cellular system. So here we can see here. So this is a full duplex node, and we have two different kind of node. One is uplink, another is downlink. They are communicating with this full duplex node. So this could be IoT node. So this one is a transmitting, and this one is a receiving. Similarly, two full duplex node, like a full duplex IoT node, they can communicate with each other. So that means they are both are sending signal to each other, and at the same time also receiving. Now these signals, the the solid line, this one indicate the signal of interest. Now there is no self interference. Okay, no self interference. So this is the ideal case. If no self interference, we can communicate. Okay, in a full duplex mode, there will no problem. But now, what is the problem? This self interference. So this one, because this one is a transmitting, same time receiving, and also here. And here the path loss will be very less, because the distance between two antennas just lambda by 2, or maybe you can, in if you have best technology. So we are in fact we are trying to accommodate more antenna and reduce this lambda by 2. That's why we are moving for a very high, massive MIMO, or where, I mean, you can bring reduce the distance between two antenna. So here there will be the self-interest signal power will be very high compared to the desired signal. So it's not easy to operate. Now, for example, you can see this is a desired signal. This is a desired signal received by this antenna. So this into this. Now this is a interference signal. So you can say self-interference. Self-interference is much higher than signal of interest. Or you can say SI means self-interference. This desired signal is much higher than 80 dB. So you can imagine, so that means the received signal power will be, the desired signal power will be very low, very low. So maybe minus 120 dB or something like. So receiver, can't decode the signal. So now here problem, now we need to control this SI or cancel this SI in a either in analog domain or digital domain. So here there is a certain assumption in a theory. Theoretically, we can assume that, let's say, this full duplex node, it knows because transmit antenna and receive antenna are at the same node. So it will know the channel, self-interference channel, and the transmit signal, and then it will simply cancel. So that is ideal case. But here, because due to this operation requires some hardware, the this antenna and the receive antenna and some signal conversion, and due to that there will be even after canceling this there will be some self interference remain in the system. That one we call residual self interference. So we need to control that residual self interference. So this is architecture of transmitter, I think, and this is a receiver. Everyone, I think, must knows this one very well. So I'm not going to uh, in detail. Now the challenges of this SI. Okay, so here we have this is a transmitted signal and this is a received signal. So so here we can see that. Okay, so here this is a received signal and this is a desired signal. Okay, YT is a received signal, and HS, this one is a transmitted from this node into this is a transmitted signal, and this is a self interference. So you can see the self interference here, and this is a received signal. So the received signal is dominated by self interference. So ultimately after quantization here Y1 you can see you will see only the interference power, or so we can't detect. So if you quantize, if you remove the interference, you will get this quantization noise. So this large Si over S will lead to larger quantization noise, and due to that now it's not easy to implement the full duplex case. Now, so the question is, how can we cancel this self interference? Okay, and how much? Okay, and how much? Let's say consider this one this example. We consider this a small cell and Wi-Fi scenario. So now let's say the transmitter here, the full duplex node. So here transmit power is 20 dBm. So from this node, so transmit power is 20 dBm. Receive SI power, here SI power is 5 dBm, and the noise level is minus 100 dBm. And the receive signal power is here, PS, desired signal power is minus 80 dBm. So what is the signal power? If you see, so this is because the receive signal power is dominated by SI. If you find the, and we need to bring this SI below the this noise level, below the noise level. If you bring below the noise level, if you bring this SI below the noise level, then your signal power will become 20 dBm. Okay, this 20 dBm. Similarly, in case of Wi-Fi, so here that means here we need to cancel 105 dB, 125 dB, and it's not possible to cancel this much in a digital domain. Similarly, in case of Wi-Fi, here we need to cancel 95 dB in digital domain. That is also not possible. So here we can see in this case, so what is SINR? Minus 85. So minus 80 minus 5. So minus 85 dBm. So this one is a receiver can't decode the signal. Similarly here minus 85 dB. But once you bring this PSI below the noise level, then below the noise level in both cases. So here we can see the SNR will become 20 dB, and also here the SNR will become 10 dB. Now receiver can easily decode the transmitted signal. So now this is a way to cancel the, I mean, motivate us to cancel the this much SI level in case of a small scale scenario or Wi-Fi scenario. Now, how can we cancel? One way is, let's say, just, if transmitter, the full duplex transmit antenna, if it uses less power, then of course the impact of on the SI or the power of SI will be lower. However, still, I mean, you can say it will dominate the complete system. So we need to cancel the SI even in that case. So how can we cancel? So there are various level. Before that, let's say compare the achievable rate in case of full duplex and full half duplex. Then we will see the some cancellation technique. So here we have a transmitter, we have receiver. In case of TDD, or here we have a small cell. So here we can see after first one is half duplex. So half duplex here SNR is 20 dB, because this will be, this is a minus 80, this is a minus 100, so this is a 20 dB. And in case of full duplex, because this self interference is dominating, SNR is minus 80 dB, signal power will become, I mean, this is SNR. So that means reception rate, here reception rate is R, here reception rate is 0. Now, but if we bring this SI below the noise level, now the SNR will become 20 dB, and here we have a certain rate, that this rate. Now we can, okay. We have, let's say, compare the this half duplex and full duplex in terms of rate. So here, let's say half duplex, because it required 2 time slot, so rate will be RRX by 2. And here full duplex, just single time slot. So this will be, I mean, without division of 2. Now, this is RRX full duplex. So here, without SI cancellation, rate will be 0. With full SI cancellation, rate will be this much. So here we can see, we can compare here SI level versus rate. So this is a ideal case, full duplex case. So if we bring the SI level below 105, so we can achieve 2 times gain over the half duplex. This is ideal case. That is not possible. So here we can do this SIC, that means SI cancellation at 3 levels. One is antenna cancellation, another is analog cancellation, and then digital cancellation. So we believe that this antenna and analog cancellation, these two, we can cancel up to 70 dB of SI, and remaining 30 to 40 we can cancel in a digital domain by designing efficient precoder and decoder. So here we can see, let's say, here this is a half duplex case, the lowest one we can see half duplex case. So its performance is very low. And then here we can go for, if you go for hybrid case, for example, this full duplex with hybrid SIC. So we have much better than this. And then we have a full duplex with full analog SIC. This is a full analog SIC, and this one full digital SIC. And this one is a hybrid SIC, both analog and digital. So we can achieve a much better performance. So meanwhile, I'm getting some questions. So should I reply now or later?
So we can take some of the.
You can complete your session, and then afterwards we can take all these questions in one go.
Okay.
You just complete your session. Okay.
Okay, so let's see SI cancellation technique. For example, this is an in-band full duplex terminal. So here, after processing at a transmitter end, so we need to transmit the signal. This is set of transmit signal. It will transmit, and again at the receiver end we are getting. And because this is at, one full duplex device, we have transmit antenna and receive antenna. And this is a nearby scattered, so there will be also self-reflection from this one as well as from this. So here you can see this will be total interference. So this one as well as the reflected paths through the nearby scatter. So here this one dominate the uplink desired signal power. So here we can cancel because we have cancellation circuit. This one is internally interconnected, so it will know the channel and the transmit signal. It will cancel completely this one. However, this hardware will dominate the performance. So we need to include that one in designing the precoder or in designing the decoder, and also this reflected paths we need to include. And this antenna cancellations, so just by separating the antenna. So here for example we have this is a transmit antenna one, and this is a another. Okay, let's antenna distance we have d, then we have a d plus lambda by 2. So this is a two transmit antenna. So by separating, if you separate, if you increase the distance, let's say between two antenna, then of course we can easily mitigate the this SI. But again, due to space limitation, we can't do this one perfectly. This is analog cancellation. So so here kind of this is a circuit requirement. We use a kind of balloon, and there will be storage of this transmitted signal. Um, and here we need to subtract this digital interference cancellation, because we are storing here this signal, and then we subtract here, and then we get the received signal, and then we decode. So again, it will require some memory to store the transmitted signal. So this also has some disadvantage, but nowadays we don't have memory problem. We can store, and then after decoding, okay, we can just update the memory. So yeah, so now up to let's say 70 dB we can decode the cancel in a digital domain. Sorry, in analog or antenna cancellation. Okay, let's say here we are going to use this machine learning technique. So for example, here we have transmit antenna and receive antenna. So set of transmit and set of receive antenna. So from here we can find the antenna correlation factor defined, and then we can pair the antenna. That means with lowest correlation factor, and then through some DNN, or so you can apply some mechanism in order to find the antenna correlation factor, and that will reduce the self interference impact. If they are highly correlated, interference will be very high. If less, then self interference will be very low. So we can apply here machine learning technique in order to find the antenna correlation factor. And then instead of using, let's say, complete transmit and receive antenna, you should uh, use subset of that, and through that we can achieve the much better performance than half duplex case. So this one we did in some of paper. So we can just you can just explore on IEEE. You can search by my name. You can find that one. Yeah. Okay, so this is a deployment scenario. So for example, here we have a two node topology, how we can deploy, like let's say IoT node, a full duplex node. Here we can deploy. So both one transmitting and receiving data from each other, but here we have self-interference scenario. So this kind of, let's say, example we can experience in D2D communication, and also the, if you have a base station or access point where we have uplink and downlink. So again, we can have like in a small cell or Wi-Fi. Another, this is a three node topology where this full duplex node, it could be access point, full duplex access point, or simple full duplex in case of device to device communication, and there could be a half duplex node. One of that will upload the data, another uh, download, or I mean this N1 is communicating with this full duplex is communicating with N2. That means this full duplex node communicating with both N1 and N2. So that means here N1 create internode interference, and there will be also self interference at a full duplex mode. So we can experience this kind of scenario in a small cell, in cellular systems, as well as the again this is small cell or Wi-Fi or base station or access point scenario. So these are the practical case. And also nowadays we can experience this one in automotive vehicular communications, where each vehicles could be operate in full duplex mode. So it send receive the signal, let's say uh, receive the signal, as well as same time it transmit the signal to the um, front vehicles and back vehicles, and also also transmitting some signal. So we are experiencing this full duplex vehicular communication. That is in a reality. And this is a very nice example, application of full duplex in order to make the system more secure, especially at a physical layer. So physical layer security, you can see where two system operate in full duplex mode, and there is a one US dropper. It wants to intercept uh, the signal of N1. Now here N2, instead of transmitting signal to N1, it generate the jamming signal. Okay? That means it transmits the jamming signal. So this jamming signal will receive by US dropper as well as N1. And N1 is transmitting genuine signal to N2. So that means US dropper, it will jam the US dropper, and also it receive the signal from N1. So this is a very nice example. So like if there is any VIP movement in your city, we can see this kind of application. Okay, for example here N1 to N2, this is a data, and N2 to N1 jamming. So the US dropper will completely block through this jamming signal. Another example we can see this cognitive radio scenario. We have primary network and secondary network. There will be a primary link. So that means primary transmitter is sending data to the primary receiver. So we have different time slot. And this is a secondary link. So here, if once primary network become ideal, that time it start transmitting signal to the to receiver. However, suppose if secondary transmitter is not sensing the activities of primary network, so there will be collision, because meanwhile primary network immediately the transmitter becomes active and start transmitting. So there will be collision with secondary network, or you can say um, uh, so there will be huge packet drop, especially for a secondary network, and also it could also impact on the primary network. So here, if we let's say convert this secondary transmitter into full duplex mode, and let's see what happened. So that means here secondary transmitter, while transmitting signal to its receiver, it also sense the primary network activities. So that means here it sense that okay, primary network is ideal. So it will increase its data rate, transmitting data rate towards its receiver. When it realized that now primary transmitter primary transmitter start transmitting, then immediately it will reduce its data rate. So based on the level of the spectrum, primary spectrum. So here you can see, here. So immediately, once he realized, because while transmitting is same time it's sensing this one, so immediately it will stop or reduce its data. So you can say we can avoid this collision. We can avoid this collision, and that means the packet loss for secondary network will be very less. So the requirement of retransmission will be very less. So in another end, we can say we can reduce the delay of the secondary network. So this is a very nice application of full duplex in cognitive radio. So here again, we can also apply now here a machine learning technique. So like for example, because we have two kind of network, primary network, secondary network, especially let's say we can apply this federated learning, multi-agent federated learning. We have let's say one agent for primary network, second agent for secondary network, and the secondary users again they train the model sent to the secondary transmitter, and since secondary transmitter is transmitting I mean operating in full duplex mode, it could uh, easily communicate with the primary network or sense the primary network, and since secondary transmitter will know the trend model, it will help in improving the spectral efficiency, as well as you can say in another term, it will reduce the huge delay for the secondary network. So these are related to full duplex case. Here we have some references. We can also get some more references, especially from IJAC perspective. As earlier I mentioned that let's say we have a dual base station or a radar base station. So the radar base station can operate in full duplex mode. So to sense the target for far field target as well as serve the users. So again, there will be self-interference. So in literature, generally we assume that in analog domain, we can cancel this 70 dB of SI, and remaining just we can cancel remaining, that means 30 to 40 dB of remaining SI in a digital domain by designing the precoder. Again, in order to design the precoder, we can, because the system will be complex. Again, this will be kind of integration of two kind of a system. So we can use machine learning in order to design the precoder as well as a decoder at the transmitter and the receiver end. And like in cognitive radio, we can because sharing of complete data with different network, it's not possible. So there we can apply federated learning, or as a beginner you can apply DQN or apply DDPG or another some other technique like PPO or modified PPO. But these are in order to publish a paper or a good paper, this has become old. So you need to move or explore some new kind of technology. So for example, we can go for personalized PPO, or similarly we have personalized federated learning method. There is a one more federated learning, and also nowadays you can also explore like AI, some new AI advanced technology for designing the precoder. Precoder, that means to optimize the or efficient resource allocation in terms of precoder power allocation and also sub-channel allocation. Since here we have a notes in the resource allocation in terms of sub-channels, like in OFDM we have a set of sub-channels. So there also we can optimize sub-channel allocation to pair the sub-channel allocation between transmitter and receiver in order to improve the performance through mitigating the interferences. There will be sub-channel interferences, inter-user, interferences. So we can control that one. So on these, all kind of problem, we can apply machine learning. So it's a very powerful tool, because once you formulate the problem, of course, the conventional method we can utilize, but again, we can't solve directly using conventional method. Either you should use a exhaustive search method, or branch and bound method, or some other method. But the complexity, if system model is at a low scale, for example, here we have 2 node or 3 node, it will work. You can use exhaustive search. There will be no issue. But imagine if we have a very massive IoT, like in a shopping mall. In shopping mall, there could be a 500,000 full duplex IoT node. How your exhaustive search algorithm will work? It can't work. So there you need to apply machine learning. That's why now AI is going to be very, very popular in all field, not only in in a computer, also in a communication. So this is a very, very powerful tool, and the devices can efficiently they can communicate and without interfering to each other. Because for AI or machine learning, they are not worried about optimization. Problem is convex or non-convex. They don't. I mean, you don't need to care about that. Just you have problem, then apply the machine learning. Just transform this one into a standard form, and then give all the input to machine learning. Then you will get the output, and that output will be um, optimal, and you can say much better than optimal. That means the same as a exhaustive search. But if you compare in terms of complexity, and if you exclude the learning time or training time of machine learning, then complexity will become very, very low compared to the exhaustive search. So that's why AI is day by day is becoming very powerful or very popular in telecommunication. Okay, so for example, large language model. Now, this is another area and we are integrating in healthcare, integrating in telecommunication. I mean, various applications. We are exploring that one. Digital twin is another part. We are integrating in a telecommunication. So we have huge scope of AI, machine learning in a telecommunication. So even the computer science graduate or computer engineering graduate, telecommunication engineering graduate can join master and PhD in telecommunication. And there is no ending, at least as I know, uh, uh, we have already we have founded, or you can say we have foundation for 7G, 8G, up to 10G. So we have predefined certain, what should be in 7G, 8G, but I'm expecting it will continue. And there will be time, I believe, once there will be time, we don't need mobile phone. So maybe our device, only the let's say smartwatch or the goggles. Now it's coming. I think Apple started providing this Facebook, or Apple, I think we started providing communication through goggles. So there will be a time when we can see, we can realize virtual screen, and like maybe you have a smart watch, and but although screen seems small, but there could be a virtual screen there. We can have the bigger screen. We can realize through smart glasses. So maybe we don't need this a smartphone in coming 15 years or 20 years later. Okay, so this was all about my talk. If you have any question, yes, we can. Uh, I can explain.
Yes, sir. We have some questions here. So first question we'll take from Dr. Baban. He has posted one question. Question is how to represent S matrix in MIMO systems.
Yes, matrix. I could not get. I mean, S matrix means what? What do you want to say?
Dr. Baban, sir, could you please clarify?
Can you repeat it?
Sir, question is how to represent S matrix in a MIMO.
I could not. Oh, oh, that is S matrix, scattering matrix. Okay.
Yes.
No, so here we have transmit and receive antenna. Okay, so this could describe we have a matrix we can define simply, let's say you can we can, let's say, by assuming there will be coupling within antenna, antenna coupling or without coupling antenna, so we can form a matrix, let's say receive into transmit, so we can form a, let's say, m by n matrix, uh, matrix. Or,
Okay, sir. And next question is why we have not tried full duplex mode of communication in earlier networks, like in case of
yeah,
3G, 4.
no, I told you it was not possible due to the self interference and co-channel interference. I means there was no technique to cancel the self interference. So like if you go back 1950, so in whole India, we had only single track railway track. Now we have a double track, three track, So with advancement of technology, now we have, we can see now we have some technique to cancel the SI as well as this self co-channel interference. So now it's possible. Before it was not possible to cancel these SI and CCI.
Okay, sir. And related to this SDN thing that we were discussing, software defined radio, right now we were discussing about that, right?
Mm-hmm. Yeah.
So, so the question on that is, do vendors, I mean, how the vendors are going to handle it, like allowing their spectrum to be used by secondary users?
Right now we are, I don't have clear idea how vendor will allow, but still because there is no agreement between, so that's why we are not experiencing this one in 5G, or so we are expecting maybe in 6G or maybe 7G. This will there again there may be shift of implementation of this full duplex in 7G. So again, there will be, once we have this like mobile devices with multiple antenna, then we can think about within the same vendor, they can provide the full duplex communication in I mean to their clients. No, his question is
Okay,
which
so none
vendor
of,
or research is currently leading the full duplex implementation globally and in. Okay, here full duplex, now there are several companies, they have made the prototype. Okay, so for example, Rice University or Stanford University, also in Edinburgh, they are also working on this full duplex. And also in Taiwan, there are a few companies, they developed this prototype for full duplex. But again, that one is only for only at the small scale, not huge users. No, just transmitter, receiver, and operate in full duplex mode. So one uplink user, one downlink user, and access point having only two antenna, one transmit and one receive antenna. At some places, they consider two transmit, two receive antenna, and two user with single antenna. So, but we are not, it will take time. Still, it will take time to realize full duplex, fully realize full duplex in a practical cases. Yes.
uh, fine, sir, fine. And sir, related to that self interference problem that we face,
Mhm.
so I mean, which out of so many techniques that we have discussed, which one is more explored by the researchers nowadays?
Nowadays,
And
you can find digital, digital beam forming. So we assume that this analog and this antenna cancellation, that this one will be provided by the vendors, service provider, I mean hardware service provider. They will cancel. They will we have some standard technique. They will cancel. So we will get the hardware. We need to develop a algorithm to cancel remaining 30 to 40 dB of SI. And in most of literature, you will find this digital beamforming based SI cancellation.
Yes, fine, sir. Participant, if you have any other question, kindly post in the chat box. We'll take it from sir. Sir has answered most of the question posted here. If anybody is having any other question, kindly post in the chat box. Meanwhile, sir, one question from my side is like, if somebody is starting the research in this field, so what would be the resources that we can explore as a beginner? I mean, somebody who's just starting his MTech or trying to explore this area.
Yeah, so see, we can find thousands of paper on this full duplex case. So it will be a little bit tough to come with some new ideas on the full duplex. And of course, but upcoming technology like IJAC, RAS, or let's say movable antenna or fluid antenna, these are very popular nowadays. And we can see, and also this machine learning, especially distributed machine learning technique, we can see, these technology in next 5 to 6 years, you know, we can find in the literature. So if someone really want to start work in telecommunication, they should start with some new technology instead of exploring the traditional one. Of course, they can do, but uh, to because if they are working on traditional one, they need to show significant improvement over traditional one, and that one is a big that will be very big problem. Of course, by changing some or developing some method, we can achieve 2% gain or 3% gain. So, but none of reviewer will agree with 2%, 3%. They will say, I mean, just to have a 2% gain, there is no meaning, to replace the existing infrastructure. So no one will replace. Even the vendor or service provider will not agree to replace their complete resources. For example, in India, now they are providing 5G, but if you see their infrastructure, they are using 4G. So they are not implementing the completely 5G infrastructure. That's why we are not getting a 5G speed. They are using 4G, just they are updating some new technology in order to just increase the speed by 10%, 20%, and just to tell the user that now we are providing 5G services.
Okay, fine, sir. And sir, actually, I tried to explore this spectrum allotment techniques back in 2014.
Mm-hmm.
So at time, most of the research papers that we were able to explore is they were talking about the sensing. So we
Mm-hmm.
had very few people even talking about using the machine learning and all in this spectrum allotment case. So since
Yeah,
I mean, when
no,
basically
this,
they started doing this.
yeah, in fact, the machine learning, from last 2 years, researchers started exploring machine learning technique. Not so you are talking about 2014. So machine learning before 2 years, maybe you could find very simple paper on DQN or DDPG or very simple method. Just in 2 years, if you see number of papers, on machine learning for telecommunication in last 2 years, especially 2023, 24, and this 2025. Now you can find thousands of paper, even more than that.
Yeah, yes. Oh, okay, sir. Nice. One more question. One attendee has posted in the WhatsApp group. what are the main factors that affect the strength of SI in a wireless system?
Yeah, so as I mentioned now, one is let's say your uh, the self-interference power, the signal power that will impact. That means transmit power of the from the transmit antenna that will impact the heavily. Another these hardware impairments like transmit impairments. Similarly, we have hardware receive impairment that will affect the SI cancellation.
Okay.
So here hardware impairment, that means because when the antenna receive the ASI signal, there will be some signal conversion. So that due to that, there may be some non-linear hardware impairment that will impact this SI cancellation. I mean the system performance overall, or this full duplex.
Right. And sir, any leading vendor who is working on these kind of things across the globe?
On of which like RIS, there are various vendors in US. Also in Taiwan, my group already made prototype for active RIS. I did MIMO communication, single user MIMO communication. And also in Taiwan, there are a few companies, they already implemented this RIS prototype they have implemented. Also was, I think in India, the one of my collaborator of VNIT Nagpur, he also successfully implemented this RIS prototype. And for IJAC, I think in China, Peking University, they already made prototype for this IJAC, integrated sensing and communication. And Heath Group in US, Heath Junior, now he is in University of California. He already made a prototype based on this millimeter wave. Yeah. So yeah, so we need to explore. I mean, because also in a Korea and also Japan, as I know, they already made some prototype. So like Docomo already implemented this multiple access technique, but up to 4 users, not for general case. And they are selling even their hardware, prototype hardware.
Sure, sir. Well, I think most of the questions are already answered now. So
So there are two more questions which they have posted now. This Ram sir, this is one more question. What could be the hazards of duplex implementation? They have written.
So I already answered this one. So
Okay.
like okay, like SI cancellation is one in an analog domain, like for how we are going to if you have let's say massive MIMO, we are converting that one in a full duplex. So how we are going to isolate the transmit and receive signal. So the placement of antenna will become very one hazard of implementing full duplex. Another, how we are going to decide the power transmit power. So in a or let's say there will be this hardware impairment, how we are going to control. So most of part we need, if we can handle in analog domain, then only we can successfully implement the full duplex case.
right. Sir, one more question is there. Can deep learning be introduced in antenna design to avoid self-interference?
Yeah, I already mentioned this, how we can use this one. So for example, let's say you have, let's say 10 transmit antenna, 10 receive antenna. So you can find out, covariance or correlated correlation coefficient between two different pairing of antenna, and then you can select the with lowest one. So that means the SI will impact will be very less because they will be more orthogonal. So instead of using all 10 antenna for transmitting and receiving, so you can use only, let's say, 4, and we can achieve the same performance as in case of 10 transmit and 10 receive antenna. So there you can apply machine learning technique or deep learning or some other method we can apply.
Yes, sir. Sure. Shilpa ma'am, I think most of the questions are answered. Shall we conclude?
Yeah, yes, sir. Yes, sir. Now we can conclude, sir.
Okay, ma'am. Okay. Yes. So thank you so much, sir, for such an insightful and enriching session. So on behalf of organizing team of this ATAL FDP, we sincerely thank you for your valuable time, efforts, and immense knowledge that you have shared with us today. So thanks a lot, sir.
Okay, okay, okay. Good night.
Thank you, sir. Thank you so much for your time and such an invaluable session. Thank you, sir. Good day, sir. Good evening, sir.